Welcome to EDU World Space.
This is chapter 21, problem number 56. We have an electron with the speed of 27.5 times 10 to the power 6 meters per second. It is traveling parallel to an electric field whose magnitude is 11.4 times 10 to the power 3 newtons per coulomb. In part A, we're asked how far will the electron travel before it stops. So we're basically asked delta x, how the distance, right? How much does this electron travel before it stops? Which means the initial velocity is given to us, right? And we know the final velocity to be 0 then, because we're asked what is the distance before it stops, right? So then actually really straightforwardly using kinematic equations, remember E final squared equals to the initial squared. Now, since it's stopping, which means the particle, the electron, is decelerating, so there is negative acceleration involved. So I'm going to put here that fact by hand, okay? 2a delta x, because the acceleration a here is negative. Then the final is 0. The left-hand side of this equation is 0. Initial velocity is given to us as v naught squared, right? So minus 2a delta x on the right-hand side, which means v naught squared equals to 2a delta x, right? So again, we're asked delta x, so if you divide both sides by 2a, we are getting delta x. However, we have an issue here. Delta x equals v naught squared over 2a, that we're not given the acceleration. We need to figure that out. For that, let's write from Newton's second law, the force acting on the electron would be the mass of the electron times the acceleration of the electron. Since now this force is due to the electric field, then it has to be, m times a has to be equal to q times e. From here, if we divide both sides by m, we can figure out what acceleration is. Then acceleration is q times e divided by m. Q being the charge of an electron, m being the mass of an electron. So let's plug this in the delta x equation. Then v naught squared over twice the qe over m is going to give us delta x. So then that equals to v naught squared times m, right, because it's in denominator, divided by 2 qe. All right, now all we need to do is, let's go up there. All we need to do is to plug in the numbers. V naught was 27.5 times 10 to the power 6 meters per second squared, right? This is v squared. Let's put m there. It's 9.11 times 10 to the power negative 31 kilograms for an electron, divided by twice the magnitude of the charge, 1.602 times 10 to the power 19 coulombs, and the magnitude of the electric field, 11.4 times 10 to the power 3 newtons per coulomb. From here, the distance traveled before the electron stops is going to be found as 0.189 meters. All right. Now, in part B, let's put it here. In part B, we're asked how much time will elapse before it returns to its starting point. So we're starting at a point, and then it decelerates at a later point, let's say A and B. We're going to look at the time that it takes, and then from B to A, it's coming back to its original position. So the total time is going to be twice the time traveled from A to B, is what I'm trying to say, right? One from A to B, and then from B to A, right? Twice the time that it takes to go from A to B, or B to A in this case. So, however you may want to solve this, let's just look at the time as we're going from A to B. How are we going to calculate this? We know that the initial velocity is, again, the initial conditions are here. The initial is v naught, v final is 0. So we can actually use the other kinematic equation that contains time, right? So E final equals V initial. Again, the acceleration is negative here as we're going from A to B. So A times t, right? So V final is 0 in this case. So V initial is going to be equal to A times T because this is 0. And we're not using V initial. Let's put, instead of V initial, let's put V naught. We're using it interchangeably anyways, right? So then for time, if we divide both sides by acceleration, these are going to cancel out. So the time is going to be equal to V naught over the acceleration, right? We know the acceleration to be QE over M, again, going back to this equation. So it's going to be NV naught over QE then, right? This is the time that it takes to go from A to B. Again, for the final answer, we're going to have to multiply it by 2. So then if we find this, well, let's go on the new page. Again, the time that it takes for this electron to go from A to B, it is NV naught over Q times E, M being 9.11 times 10 to the power negative 31 kilograms, V naught being 27.5 times 10 to the power 6 meters per second, divided by 1.602 times 10 to the power negative 19 coulombs. The electric field is 11.4 times 10 to the power 3 newtons per coulomb. So the time is going to be 1.375 times 10 to the power negative 8 seconds. So for the total time then, we're going to have to multiply this by 2. 2 times 1.375 times 10 to the power negative 8 seconds is going to be equal to, well, 1.375, it's 275, right? 275 times 10 to the power negative 8 seconds is the total time it elapsed.